Hello, everyone. We will be starting right at 12:30. All right, good afternoon and welcome to the SAF's Quantitative Seminar. Thank you for joining us today. I'd like to start by acknowledging the Coast Salish peoples of the land. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. And now it's my pleasure to introduce our speaker for today, Andrea Havron. Andrea is a statistical ecologist currently working as a postdoctoral fellow at the University of Washington under Andre Punt in conjunction with Carrie McGillard and other NOAA staff at the Alaska Fishery Science Center. She earned her PhD in statistics from the University of Auckland, where she specialized in developing spatial models using TMB. She earned a GIS certificate and a master's in marine resource management from Oregon State University and a Bachelor of Science degree in zoology from North Carolina State University. Andrea will be starting a new position next month working on the Fisheries Integrated Modeling System Initiative as an ECS contractor. And now, Andrea, go ahead and you can take it away.
Thanks, Megan, for the introduction, and thanks everyone for coming today to this quantitative seminar. I'm going to be discussing the work that I've been doing for my postdoc project with Andre Punt and Carrie McGillard at the Alaska Fishery Science Center and University of Washington, where I've been working on developing a new spatial finite mixture model and turning that into an R package that I'm calling clustTMB. So before diving into what exactly is a spatial finite mixture model, I thought I'd just revisit the concept of a continuous spatial model. And this is what we'd frequently encounter when we're running models using, for example, VAST, where we have a continuous spatial process that we're trying to determine the mean trend of the process along with the spatially correlated error structure. And these are typically fit using random effects models where the spatial effect follows a multivariate normal distribution with a zero mean and a covariance matrix that captures the spatial correlation decay among the pairs of locations throughout the landscape. So this works great when the spatial process is continuous and smooth, but oftentimes in ecology, we can run into situations where the spatial process has discrete discontinuities. And that can occur if we're thinking about ecological patch networks. And for example, if we're looking at the bathymetry of the Gulf of Alaska, there are a lot of potential processes that can introduce discontinuities or sharp edges to our spatial process. And here, when I'm referring to spatial process, we can be thinking about this as a covariate that has a spatial structure that's not being observed, or it can be some sort of spatial process inherent in the biological system. And so we can encounter this if we have unobserved spatially discrete covariates that are informing our information. But we can also encounter situations where we have discrete spatial processes in the context of spatial management, where we can run into situations where if we're looking at fishery observation data, where there are discrete discontinuities in the process due to hard edges and shapes to the management system itself, where there are spatial closures or regions where fishery operations will change their behaviors. So in this situation, we might want to consider looking into the applications of discrete spatial finite mixture models, where we can consider discrete spatial patterns where we have an unobserved cluster identification, a latent ID that follows a multinomial distribution where the probability that a given observation belongs to a particular cluster can be based on a set of covariates and a spatial random effect. Within each cluster, we can also have unique distributions. These unique distributions can potentially have spatial structure to them as well. So diving into what a finite mixture model entails, we'll first look at the general concept of the finite mixture likelihood. And that's that we can express this as a marginal likelihood of the product of the sum of the cluster, the probability of cluster membership, pi, multiplied times the likelihood of the distribution. And this is employed throughout statistics for when we're dealing with multimodal data, where essentially we have observations from two distributions, but the identity that an observation belongs to a particular distribution is missing. It is considered latent. And these models are typically handled using an EM algorithm, where there's a step where the cluster identity, Z, is marginalized using this framework. We can calculate the marginal cluster identity Z using a posterior probability of cluster membership. That's this ratio in the center here. It's essentially the ratio of the marginal likelihood of each cluster over the sum of all possible marginal likelihoods. Then we can identify the marginal cluster ID, and we can assign that based on the maximum value of this Z hat ratio. Using this marginal cluster ID, we can then calculate the conditional likelihood, which is the sum of the probability of cluster membership multiplied by each unique distribution raised to the power of that latent cluster ID. So when we take the log of this conditional likelihood, it becomes a much more amenable likelihood to work with in optimization framework, where we're essentially multiplying this matrix of ones and zeros by our marginal likelihoods. This allows us to, the only marginal likelihood that enters into the conditional likelihood is the one associated with the cluster that was maximized during the marginalization step of Z. So as I said, these types of models are typically handled using the EM algorithm. However, there are also expansions of the finite mixture model into the Bayesian context, into using MC methods. I developed a new finite mixture model using Template Model Builder, and this framework uses automatic differential software, applying generalized linear mixed models where we can have fixed effects and random effects. And the random effects are marginalized out by calculating the Laplace approximation. A nice aspect of Template Model Builder is there are a lot of great spatial modeling capabilities that allow for quick and efficient estimation of the spatial likelihoods. Now, Template Model Builder, the Laplace approximation is only appropriate when our latent variables are continuous. And in the case of the finite mixture model, we have that latent ID Z that is discrete. And so rather than use the Laplace approximation, the model that I set up with clustTMB is set up so that the marginalization of Z is calculated explicitly within the code. So going through the steps taken in clustTMB to fit a spatial finite mixture model, we have the continuous latent likelihoods specified in the model. Then the observation likelihood for each cluster is identified. So for each cluster, we have a unique distribution, and we calculate the marginal value of that latent cluster ID explicitly within the code. And after this step, the conditional likelihood is specified, which is then entered into the optimization process in TMB. So the nice aspect of using clustTMB is that it offers a lot of flexibility outside of the MCMC land, where we can introduce new extensions to the finite mixture model process. And so just a quick overview of what different extensions can look like in finite mixture models. We can have covariates that enter into the model either by informing the probability of group membership, Z, or by informing the mean of the distribution itself, or both. And I'm going to just briefly introduce some of the terminology used in model-based clustering literature, and that's the whenever a covariate or random effect enters into the finite mixture model, we can refer to this as a model of experts. And when the covariate is informing the probability of group membership, as we see here on the bottom left, that's considered a gating network, whereas if the covariate is informing the mean of the distribution, that is considered an expert network. And when the expert network is essentially employing a mixture of regressions. And when we have the covariate informing both the probability of cluster ID and the mean of the distribution, we refer to this as a full mixture of experts. So going through each of these in turn, if we have just our general finite mixture model, where we do not have any covariates informing any component of the model. Again, this is our marginal likelihood up on top, and clustTMB is used to set up a model following similar syntax as other model-based clustering R packages, such as mclust or MOE-clust. And essentially we have our response is specified along with what's called the gating formula and the expert formula. And again, this is determining the gating network and the expert network. In this situation where the covariate isn't influencing either, we would just set both of these formulas to be intercept only. We can specify families. We specify the number of clusters that we're detecting in the model. The value of the number of clusters is essentially determined through a model selection process using BIC. This final line covariance structure is identifying the covariance structure of the observation likelihood. So if we have a multivariate Gaussian, a mixture of multivariate Gaussian distributions, the covariance structure is defining how the covariance of that multivariate normal is set up for each cluster. And this again follows similar notation in model-based clustering literature, where VVV is used to specify that we're estimating all the off diagonals of the correlation matrix, as well as unique variances for each column of the response and each cluster. When we have the covariate informing the gating network, again, that is the covariate is informing this probability of cluster membership through logistic regression. Then we can set up the gating formula to be a function of X, and we also have to specify the gating data so clustTMB knows where to look for this information. For the expert network, essentially the covariate is informing the mean process of the distribution through some link function, and we update the clustTMB syntax using expert formula and expert data. And finally, the full mixture of experts, when the covariate is informing both the gating and expert networks, you would update both of those formulas and both of the data matrices. So in clustTMB, we can handle all these covariate, all these scenarios, as well as include random effects components in both the gating and expert formulas. And so far, the current version of TMB accepts the following random effect structure. Uses a spatial Gaussian Markov random field process if we want to include spatial random effects in the gating or expert networks, an AR1 process for any temporal components. It also implements a rank reduction. And if we have a response matrix of, say, I observations in J columns, where J could represent species, if there is some sort of correlation among the residuals, we could reduce the dimensions of the J columns down to an independent number of F factors of the random effects would be reduced from J columns down to an independent number of F factors. And this is referred to often as rank reduction, and it's implemented both as a random rank reduction, where there's no correlation structure to the error, is simply a multivariate normal, and a spatial rank reduction, where these spatial random effects can be reduced from J to F factors. And here's just several examples of how these different random effect structures can enter into the formulas. With AR1, here we have the Gaussian Markov random field entering into the expert formula and a spatial reduction specified on the expert formula. So rank reduction can only be allowed in the expert formula. In here, there's also a change to the covariance structure. This is essentially identifying a diagonal covariance matrix in the observation component of the distribution, and also updating a spatial list where we specify the locations, and this is an inlaw mesh that can be provided to the package in order to determine the structure of the random effects matrix. And looking at number of distributions, I've added several continuous distributions to clustTMB. The Gaussian is sort of the standard distribution used. The covariance structures can be general, where we estimate all the off diagonals as well as the variances, and a diagonal where we're only estimating the variances but not the correlations. The same for log normal. I've also included a gamma and a compound Poisson gamma distribution. For those not familiar, the compound Poisson gamma is a distribution with a peak of observations at 0, and then if values are greater than 0, they follow a positively skewed distribution. And it's a useful distribution when fitting fishery data. And so both the gamma and the compound Poisson gamma don't have a straightforward multivariate form, and so these can only be estimated as diagonal distributions, IID. And so I'm going to shift gears after kind of going over this description of the package. I'm going to shift gears to look at simulation examples and an example of case study using fishery data. Before I do so, I just wanted to open the floor to see if anyone had any questions about the package itself.
I don't see any questions right now, Andrea, but we'll take them at the end or your next break.
Yeah, we'll just move on. And so I developed a simulation run to test the performance of clustTMB and compare it to a commonly used model-based cluster tool, mClust, as well as several algorithmic approaches to clustering, like k-means, PAM, or Ward. And I essentially generated 50 simulations of 1,000 samples and 4 simulated species. I used 3 clusters in the true data and repeated this for data that was both Gaussian distributed and the compound Poisson gamma. And I mentioned the Tweety here, as clustTMB uses the Tweety distribution family with a constraint on the power parameter to range between 1 and 2. I included spatial random effects to only enter into the gating network, and I included 4 levels of distribution overlap. And so the distribution overlap is essentially simulating data with different levels of area overlap between the clusters. So the far left here, the overlap is 0.3, where all the clusters are highly essentially overlaid on top of each other, versus a smaller overlap where there's a lot more distinction among the different clusters. So when fitting these models with clustTMB package, on the left is an example using the Gaussian distribution, on the right the compound Poisson gamma, again using the Tweety distribution family. And I apologize, there's an error, that should be link equals log for the Tweety. I'll make sure to make a correction. And so on the left, for both distributions, we have the spatial effects in the gating formula. And I fit clusters ranging from 2 to 5 clusters for each model, and used BIC to select the most optimum cluster for mclust and clustTMB, and used a silhouette metric for the algorithm approaches. And on the left, our multivariate normal Gaussian distribution was had an unconstrained off diagonal, so we were specifying all the correlations between the responses. And on the right, the compound Poisson gamma had an IID distribution. So looking at results from a single simulation, we can see on the left is the true classification of the data, whereas on the right is the predicted classification. And here's an example of all of the actual simulated data, where on the top is the true values and on the bottom is the estimated values. And again, there was only spatial random effects entering into the gating network and not the expert network. So the bottom plot is just showing the estimated mean value for each cluster. And these are 4 plots representing the 4 simulated species. If we want to consider performance results, we can look at 3 different metrics commonly used in assessing the performance of cluster models. Ranging from the top is the adjusted RAND index, which considers the accuracy of class assignment. The middle is class agreement proportion, which uses set matching to compare the estimated cluster against all possible permutations of clusters. And at the bottom is variance of information, which is a mutual entropy metric of the comparison of pairwise class comparisons. And so we can see on the left, we have the range of mclust+TMB is this lighter brown color, and then we have 3 algorithm approaches to clustering: k-means, PAM, and Ward. And in general, the clustTMB and mclust at small levels of overlap perform much better than all the algorithm approaches. But as we increase the overlap between distributions, the clustTMB model is outperforming even mclust. And if we do a pairwise comparison of mclust versus clustTMB, where higher values are good for AR and CP and lower values are better for variance of information, we can see that pairwise comparisons also show that clustTMB is performing better than mclust. And looking at the CPG spatial mixtures, again, on the left is the true class, on the right, the predicted class. And on the top, the true distribution of the data, on the bottom, the predicted distribution of the data. So even when working with the CPG spatial mixture models, we're also getting fairly good results. And similar trends where at small levels of overlap, mclust is doing a pretty good job of depicting or isolating the 2 clusters, but once the overlap is increasing, clustTMB is outperforming mclust. And the additional benefit of using clustTMB is because we have spatial information informing the clusters, we can get predictive maps of cluster membership. So just another brief pause for questions. I noticed there's a question asking about if the package is available on GitHub. It is not yet available on GitHub, but will be available soon. That's one of the goals of the next month, is to get that online. So moving on to an application of this package to the Bering Sea multi-species groundfish fishery. I originally developed this package to address an issue that I was looking at with a management strategy evaluation of the multi-species groundfish fishery in the Bering Sea and Aleutian Islands. And essentially the MSE was looking at was grouping the fishing fleet into a structure based on métiers. And a métier is essentially a group of fishing operations that are targeting a similar assemblage of species, similar gear, similar times of year or area. And the idea is to attempt to put some sort of structure on the fleet that can be used in an MSE context. And previously, work done on this MSE had used the k-means algorithm to cluster the data. And essentially, the métiers that were defined from this cluster analysis were static over space or static over time. And so essentially, there was interest in looking at how the cluster membership could potentially, or the métier membership could potentially vary over space and time. So just a brief overview, the Bering Sea multi-species catch composition is pretty diverse. There's, it's highly dominated by pollock, but there's a lot of other species that are caught in this multi-species fishery, including cod and a number of flatfish. And so I think the important thing here is just that this is a very diverse fishery, and that there are a number of different sectors involved in this fishery that each target different collections of species. And so the idea is to look and consider how the composition of these species in catch composition is changing over time, and how that is potentially also being impacted by the catch of Pacific halibut, which is considered to be a constraint in the groundfish fishery, where the groundfish fishery is harvesting halibut that are a younger age and smaller than what is being harvested by the direct halibut fishery. And so typically in the groundfish fishery, the halibut is treated as a constraint to the system. So I'm going to run an example showing you results from using the cluster package, the clustTMB package on the A80 fleet. This is the Alaska Seafood Cooperative, formed in 2008 under Amendment 80 regulations. They use bottom trawl gear and primarily target flatfish and Pacific cod. And they do have an allocation for Pacific halibut. So when setting up this model, I did a cluster analysis on a subset of 4 species: Pacific cod, halibut, pollock, and yellowfin sole. I included a spatial effect in the gating network and used the IID Tweedy family. I ran 3 separate models for the years 2010, 2012, and 2014. And looking at results, we can see that there is indeed a spatial temporal structure to the clustering of the fleet, where in 2010, the catch compositions are heavily dominated by pollock, and in 2012, we can see that contribution of pollock to the gray cluster drops significantly, and the red cluster as well, whereas it still is somewhat contributing to this blue cluster in the middle of the Bering Sea region. And that shifts again in 2014, where we see a dramatic decline in the proportion of pollock in the blue clustered regions. And interestingly enough, the red clustered region has a low biomass proportion of biomass contribution to the entire system. And so from this example, we can see that this model can be a useful tool in detecting spatial temporal clustering of the Bering Sea fishing fleet. And we can use this as like an exploratory tool that helps identify potential covariates that drive the clustering patterns in the fleet, and can be used to guide the spatial temporal structure of métiers in management strategy evaluation. So future work, I see pursuing this spatial temporal cluster analysis of the Bering Sea and Aleutian Islands fleet, and to expand this analysis to include more sectors and species, and explore different covariates and random effects in the gating network. And the idea is essentially to identify covariates that are useful in determining spatial temporal structure of the fleet that can be used to inform management strategy evaluation. And as I mentioned before, this clustTMB package should be posted soon to GitHub, and I have included my GitHub address. All right, thank you so much. I'd like to open it up for questions.
All right, Andrea, thank you. That was an excellent presentation. And just a reminder, the audience can type their question into the chat box, or if you'd rather just ask it directly, then go ahead and raise your hand and I will unmute you. And we have a question from Mark. Let me pass this on to Andrea. Okay, Mark says, thank you, so cool. I think I'm lost. What is the response Y in the fisheries example?
Oh, thanks for your question. Yeah, I might have gone through that a bit fast. So yes, the response Y is going to be for the A80 Fleet. I ran this model for 3 separate years. So it would be essentially a subset of Pacific cod, halibut, pollock, and yellowfin sole for the first model for year 2010, and looking at the biomass or the weights of each species. And so that's going to be a matrix of zeros and positive catch values that enter into the Tweedy distribution, which again, it has allows for a peak value of 0 and a skewed positive distribution. And so this is a multivariate data set. So number of observations in 2010 for 4 different species.
Okay, and we have a question from Howard Stiff. He has his hand raised. And so Howard, I'm going to unmute you. So now if you click on the microphone button on your screen, you should be able to talk and ask your question.
Thanks. I didn't think I have a question, but now that you've asked me, I will ask whether there were some environmental factors that you were using to characterize the spatial network or spatial distribution in any way. In other words, is this simply based on spatial effects, or were there environmental factors also involved?
Thanks for your question. So at this point, it's only including spatial effects, but the idea is to identify covariates that are significant in driving the clustered distribution patterns. And, you know, considering the fact that this eventually wants to be, results from this want to work into an MSE context, it would, in that sense, having fixed covariates that inform cluster distributions would be more useful to the MSE context than spatial random effects. So at this sense, at the level that it's at right now, it can be used more as an exploratory tool to help identify if there are any covariates useful for that purpose, and also to further along bring in covariates to inform the gating or the expert formulas as well.
Thanks. Amazing.
Okay, and now we have a question from Christine. Christine asks, can you talk a little bit more about how you decide on which structure to use for the variance covariance matrix?
Yep, that's a great question. So the, see if I can quickly go back to the slide that details the distributions. So I list here general, diagonal, and essentially, again, just a quick review, the covariance structures are modeling the variance covariance matrix of each observation distribution, the data distribution. And so we can have a general structure where we're estimating the variances on the diagonal as well as the correlations on the off diagonal. And this can be a single covariance matrix that is the same value across all clusters and species, or it could be set to vary by cluster or by species. And essentially, you can use model selection to determine at what level of complexity you need the covariance structure, because we're adding parameters as we, you know, a general matrix where we're estimating all the off diagonals is going to have a lot more fixed parameters than a diagonal matrix. And so we can just use model selection to choose which is the most appropriate covariance structure.
Okay, and then the next question is from Kelly, and she asks, how likely is it that the algorithm picks up clusters when they don't exist? Do you look at the results from just a single, or did you look at the results from just a single species with no clustering?
At this point, no, I haven't, but that's essentially a very important null model that needs to be considered. And I think that's how you can essentially answer that first question is how likely can this algorithm pick up on clusters that didn't exist? And that is always a danger when we're running finite mixture models. But essentially, whenever you run this type of analysis, you always need to have that null model where you're assuming there are no clustering structure to the data, and it's all just from a single distribution. Does that answer your question enough, or were you interested in more details?
I don't see a follow-up question. Oh, she says that she'll email you.
Okay,
and
perfect.
yeah. There is a question from Karen. She asks, is there a way to determine the number of optimal clusters using clustTMB?
Yeah, so the recommendation in model-based clustering literature is to use BIC to select the most optimal number of clusters. So it's just a matter of running a number of different models with the value of cluster specified for each model, and then looking at the BIC to compare as a selection tool.
Okay, and Karen says thank you. I don't see any other questions yet in the queue, but we'll keep it open for a little while longer, just in case something comes to mind. And I just want to remind everyone too that this talk will be posted on YouTube channel. So if you want to go back and review it, it will be up there in the next couple of days or so. Okay, here's another question from Christine. She asks, did you look at how the clusters change in the Bering Sea for years in which the cap is hit versus not hit?
I have not, but that is definitely a really interesting suggestion to take a look at that.
Okay, and Christine says thank you. All right, well, this was really informative talk. Looks like a lot of work went into it, and it looks like we'll probably be able to find a lot of good applications for it. Thank you for giving us your time to present this to us, Andrea.
Thanks so much for having me. I enjoyed being part of the QuantSem.
Thanks. Have a good weekend, everybody. Hey, Andrea, are you still on the call, on the talk? I don't think she is. Yeah, Mark, she's already left. Okay.